Urban centers face increasingly unpredictable environmental threats. Plumes of wildfire smoke or construction dust can saturate an entire city in a matter of hours. To track these events, we rely on government reference monitors. These stations are highly accurate, but they are too expensive to place on every corner, leaving massive gaps in our street-level data. Meanwhile, cities are investing millions of dollars into urban greenery to combat heat and air pollution. These trees are constantly absorbing toxins, but they don't report back. They are silent assets, a huge financial investment that provides no data. Knowing the chemical makeup of the air doesn't reveal the damage it's causing to the environment. To close that blind spot, we have to measure how the living ecosystem is actually responding. This requires plant electrophysiology. While plants don't have a nervous system, they react to environmental stress by firing off measurable electrical impulses. Specific stressors like heavy metals or ozone trigger action and variation potentials, electrical waves pulsing through the plant's vascular tissue. We capture these signals by inserting microelectrodes, continuously monitoring tiny voltage shifts. Machine learning models then process these signals, identifying distinct stress signatures. However, in a city, a biological spike on its own is an alarm without an explanation. We can't tell if the plant is reacting to toxic gas or just the vibration of a passing truck. This noise problem makes standalone biological sensing unreliable in a chaotic street environment. The solution is a second technology track, abiotic sensor nodes mounted on the daily routes of municipal fleets, like postal trucks. As these vehicles run their normal routes, they generate high-resolution environmental data for every block they pass. By layering this street-level air quality data directly over the biological signals of the instrumented trees, we create context. For example, a mobile fleet might detect a localized plume of silica dust from an active construction site. The AI cross-references that spike with a downwind tree that is simultaneously registering severe stress in its stomata. This fusion creates a calibrated biological sensor, capable of distinguishing specific pollutants from background city noise. This shifts the role of urban greenery. It becomes the living grid, an interconnected biological nervous system for the city. Municipalities can use this fused intelligence to track the specific ecological impact of industrial sites or port emissions. Because the data measures the actual physical response of the ecosystem, it provides the ground truth required for real estate emissions reporting under laws like New York's Local Law 97. Urban forestry departments can use these block-by-block maps to select and plant specific species that are proven to thrive in that exact chemical environment. This turns a passive park budget into a recurring data asset. Insurance carriers and real estate firms can subscribe to these feeds to quantify localized environmental risk at the address level. Fusing biology with street-level data creates a queryable interface for the biosphere, turning the entire urban forest into a functional data product.